Hi, in this video, we're going to take a look at full factorial design of experiments. Okay, so in full factorial designs, what we're trying to do, we're trying to capture all possible combinations of all of our interesting factors to get the most complete information possible. Now, this is very, very powerful because I get the most deep into the weeds aspect of my data. I get as much analysis as I possibly can, and I set this up with my design experiments to get as much bang for my buck as I possibly can. Now, there's a major disadvantage with full factorial designs in that it takes a lot of data to the point that it usually isn't feasible for me to actually do a full factorial design. All right, so what I'm doing is before I set up my experiments, before I collect my data, before I do anything like that, I'm going to do the pencil and paper mathematics to get the best possible experiments beforehand. I'm coming up with my experiment game plan to get a good solid results so I can get the best bang for my buck for my data, for the time, money, and effort I put into it. Okay, so I'm setting up, I'm figuring out what am I going to set the levels of my independent variables before I run my experiments. Then after I figure this out, I'm actually going to run my experiments with the levels that are set up during the pencil and paper mathematics, and then I'm going to record the dependent variable values. Okay, so full factorial designs, we cover all possible combinations of our independent variables. The advantage is that we can capture all possibilities. And so this is very powerful. This gives us the most in-depth look at our results as we could possibly hope for. We take it as far as we can. So we can do full analysis. Every way you could possibly imagine is covered, and we can capture interactions. And that includes higher order interactions like three-way interactions, four-way interactions, and so on. Now, there's a cost. And that cost is that this requires a lot of data. Even with just one iteration for a unique level of combinations, we need a lot of data. The minimum amount is going to be 2 to the power of n, where n is the number of factors I've got going on. And so this is a lot, it grows exponentially. The amount of data needed makes it so that usually we only study a few independent variables to reduce the number of observations that we're going to do. And also, we typically only do 2 levels for our independent variables when we do when we do full factor analysis. The reason for this is just to reduce the number of levels I can deal with. Now, if I have a numeric independent variable, in this situation, I'm going to take 2 extreme values, one far to the left on the number line, one far to the right on the number line. Both are reasonable for the purpose of the experiment for our subject matter, and just do those 2 levels. I'm not going to have a grid going on because that would lead to more experimental runs that I don't have the time, money, and effort to do. All right, so why do we do this? Why is this interesting? Well, from a math point of view, so now we're going into the math world of why this is a good idea. Well, this ends up giving us a design matrix that has like a lot of nice mathematical properties. And these mathematical properties we can use to get more powerful analysis with fewer observations. First and foremost, our design matrix is going to be full rank. It's going to have full span. And all you linear algebra fans out there, our design matrix is going to have a matrix inverse. Now, to set this up, I'm going to include the intercept as all ones in my design matrix, by the way. All right, well, we're going to have orthogonal columns. So if I take the dot product between any 2 columns, I'm going to end up getting 0. So that is going to give us more informative value. So that means that we're going to have 0 correlation between our columns, our predicted variable columns. And so that it's going to be easier for us to interpret things, and we're not going to have to worry about any correlation issues. So we're going to have orthogonal matrix. So all the columns are going to be perpendicular to each other in terms of the dot product. Now note that it's not orthonormal, that these will not be orthonormal matrices, except for in the trivial case. Now, here's something that's going to be interesting with how I set this up. Every column, when multiplied by itself entry-wise, gives the intercept column. What I'm going to do, I'm going to set up that in my design, I'm going to have -1 for the low level, 1, +1 for the high level, and that's going to be how I set up my design matrix. And I'm going to have a coding between the -1 and 1 to the high-low values. All right, well, when I multiply a column by itself, and that's entry-wise multiplication, I'm going to get the constant 1 column, which is going to be the intercept, which is going to be important when we get into the group theory aspect of design of experiments. Now, the entry-wise product between any two columns gives another column on the design matrix. All right, so this is called closure under the multiplication from a group theory point of view. Also, to go take it even further, if I take any two columns, there's going to be a third column that if I multiply the first by the third, I'll get the second 100% of the time. All right, so that means I have, with a little bit of, mathematics, we can show that this forms an abelian group. All right, well, why do we care about that? Well, that means I can invoke abstract algebra to get more powerful analysis when we start doing partial factorial analysis down the road. We'll talk about all this in a later video. All right, since the columns are orthogonal to each other, that is what I multiply the entries together and then add up the products, I'm going to get 0. All right, that means I have 0 correlation between my columns. This makes interpretation easier. Also, on the design matrix, the average is 1 for the intercept and 0 for all other columns. So we have 0 mean for all non-intercept columns, which is nice. Okay, so let's go ahead and start using R to help us build our design matrices. So I always like piping, so I'm pulling in the Magritter package. And then, just to make sure I don't have too many digits, put the 3, avoid scientific notation. All right, so first one I'm going to show is the 0 factorial design. All right, the 0 factorial design is where I have no independent variables. Here, I would be running the same level of observation over and over and over in my experiment, and it's just fixed and it's static. This corresponds to just doing a level just to run it over and over and over, which might be useful, for like calibration or just initial look, just to get an idea of how things are going to go to make sure the logistics work. All right, and so this is and the reason why I'm showing this here is just to be complete, just to show that, to be mathematically pick up the full range of what's possible from a math point of view, not necessarily from an actual scientific point of view. I'm including this. All right, so M0 is my design matrix for a 0 factorial design. I have no independent variables. I just have the intercept. And this would correspond to, I set up levels of an experiment and just one type of observation for my independent variables, and then I just run this over and over and over. That would correspond to this. Now, a 1 factorial design, I have one independent variable, and I'm going to call that A. And it's got 2 levels I'm interested in, -1 for one level, 1 for the other one. Okay, so if I have just 2 levels like male, female, high, low, yes, no, this is perfect. If I had numeric values for my actual real life experiment, so my independent variable is numeric, when I run my experiment, I'm going to have a high and a low level. And I'm setting this up so that the -1 corresponds to the lower value, low but realistic. 1 is high but still realistic, not like, not like something major extreme, something that I could actually observe in a real situation, but on the high end of it, on the low end of it. Okay, so here is my first non-trivial design matrix. All right, we see we have the intercepts are all 1, and then I've got -1 and 1 for this. And when I do my design matrix at this stage of the game, as I was talking about the concepts, we're just having unique rows. We don't have any replication of the same level multiple times. We'll talk about that towards the end. Okay, so notice that if I go through and I multiply the first column by the second column, I end up getting the second column. 1 times -1 is 1. 1 times 1 is 1. All right, so if I multiply these together, I get -1 and 1, and that is the column A. Okay, if I multiply the A column by itself, I get -1 times -1, which is 1. 1 times 1 is 1, which is the intercept. Huh, kind of interesting. And the intercept by itself is the intercept because it's all ones. That's not really that interesting. Okay, so this is my simplest design that I possibly have with an actual factor being involved. Let's make this a little bit more complicated. Something I need to say. Notice that the dimensions are square. This is a 1 by 1 matrix. This is a 2 by 2 matrix. Our next one is going to be a 4 by 4 matrix. Notice that it's square and the dimensions are powers of 2. That's not a coincidence. Okay, so let's say that I have two factors I'm interested in, A and B. A has a high and low level. B has a high and low level. All right, so when I set this up, I've got my intercept column going on here, all ones. I have my A column, and you'll notice that A alternates between -1 and 1. B is -1 1 also, but it's a different pattern. I have -1 1, -1 1, -1 -1, repeat the -1, then 1 1, repeat the 1 as I go down. Okay, so you can see that all possible combinations of A and B are achieved on this matrix. All right, well, what would happen if I multiplied these two columns together? All right, -1 times -1 is 1. -1 times -1 is -1. -1 times 1 is -1. And then 1 times 1 is 1. You'll see that I've got this multiplication going on to give me that. Okay, that should be an assignment arrow, not an equal sign. I feel bad about myself for doing that. I will fix that before lecture. Okay, so now you'll notice I've got a 4 by 4 matrix. All right, so the dimensions are 2 to the power of 2, so 2 to the power of the number of factors. And this is a full rank square matrix. It has an invariable, and the columns are orthogonal to each other. You'll notice if I go through and I multiply the entries together of any two columns and then add it up, I get 0 every single time. I have 0 correlation between my columns. All right, now we'll give you 3 factorial design. All right, so let's kick it up a notch even further. Let's get C involved. Now I have 3 factors that I'm interested in. And I'm going to go through and do the same game I did before. Intercept is all ones, going all the way down. A alternates between -1 and 1 as I go all the way down. Now B goes twice -1, twice +1, twice -1, twice +1. Now C does 4 times of -1 and then 4 times of +1. Look at that. So all possible combinations of A, B, and C have been achieved. So if I have 2 levels for 3 different factors for my experiment, I've got all possible combinations achieved. Okay, so now what about the intercepts? Well, the intercepts, just like I did before, is I'm going to multiply the columns together. If I take -1 times -1, I get +1. 1 times -1, I get -1. -1 times 1, I get a -1. I get 1 times 1 gives me +1. -1 times -1 gives me 1. 1 times -1 gives me -1. -1 times 1 gives me -1. And then 1 times 1 gives me 1. So all possible products of A and B are achieved in this column. Same thing for A and C, B and C. Now, I have to take it a step further. I have 3 factors, so I potentially might be interested in 3-way interactions. So I need to multiply A times B times C. And you'll notice I've got that right here in this column to the far right. Also, notice that if I walk up and I multiply a column by itself, it's automatically going to be the intercept because I have all ones and negative ones. And test me out. See if you can see if you don't trust this. Take any two columns, multiply them together entry-wise. You will always get a column that is on the matrix. And so go do that. Check to see, like if I take, see, AC times BC, let's see, what do I get? That's a 1, -1. Let's see, where would that be? I think it's going to be AB. Yeah, then -1, +1, +1, -1. Yeah, then -1, and then 1. If I take AC times BC, that actually gives me A times B. Huh, kind of interesting. Okay, so now I told you that we have all these different properties are really slick and really great. So I want to verify it. So I want to prove to you that this is actually the case. So what I'm going to do, I'm going to set up a list of all these matrices. I'm going to go through, I'm going to show you all the dimensions, then I'm going to show you all the ranks. All right, so here with the dimensions, I can see that for my 0 factorial, 1 factorial, 2 factorial, and 3 factorial, we have dimensions 1, 1, 2, 2, 4, 4, 8, 8. Okay, so notice that each time it's 2 to the power of the number of factors that I've got. It's square every single time. So that's just the dimensions. Let's check that they're full rank. If it's full rank, the numbers I'm going to see are going to be 1, 2, 4, and 8. Do we get that? Hey, look at that. 1, 2, 4, and 8. Boom. Check that out. Okay, so we know that we have full rank matrices. That's definitely important. Now let's go through and show that every column is orthogonal. So here we have orthogonal matrices as if I take a matrix, multiply by its transpose, since we're dealing strictly with real numbers, I'm going to end up getting a diagonal matrix. Now, it's not orthonormal. Orthonormal would mean that I would get the identity matrix when I multiply by itself. All right, so I'm going to walk up. I'm going to take my design matrix as a matrix instead of a data frame, and I'm going to multiply itself by its transpose. And notice I get diagonal matrices every single time. All right, the first case is trivial. That's, doesn't really matter. But now see, I've got a 2 by 2 matrix, and it's a diagonal. I have a 4 by 4 diagonal matrix. I have an 8 by 8 diagonal matrix, and you'll notice that the number of observations in the design, distinct observations, is what's on the diagonal every single time. Okay, so what this shows is that if I go through and I multiply any two columns that are different from each other, I get 0 every single time. Only time I don't get 0 is when I multiply a column by itself. And when I do that, the dot product is going to end up being the dimension of the matrix. Okay, that's kind of interesting. All right, so let's kick it up a notch. What we're going to do, I'm going to show you, go through all possible combinations, and I'm going to demonstrate to you that if I multiply any two columns together, I'm going to get another column on the design matrix. Okay, now first thing I'm going to do is I'm going to relabel the intercept column as E. E is what I learned as the identity element in group theory. So I'm going to call the intercept E for that reason. Now I'm going to go through, I'm going to extract the column names, and I'm going to set up something called a Cayley table. A Cayley table, you can think of it as like a multiplication table or an addition table, like from elementary school when you had to memorize all the different products and sums. This is for, but a Cayley table is for like a group or a ring or a field that we're working on. So it's more general than what we did in elementary school. But think of it as like a multiplication table for a different mathematical structure. Okay, so now what I'm going to do, I'm going to take the product of every possible pair of columns. And I'll do column 1 with column 2, column 1 with column 3, column 1 with column 4. I'll keep on going through all possible pairs. And I'm actually going to do all possible pairs twice, because here I'm going to take the point of view that order matters. That's important for non-commutative group theory. Here everything's commutative, but I just want to be consistent. All right, and so what we're going to do, if I take B times AB, I get column A. If I take AB and I multiply by ABC, I get AB. Okay. And so first thing I want you to notice is that every single column appears in every single row. Every single column appears in every single column. So if I go through here, I see that I have E, the main effects, the two-way interactions, and the three-way interactions. If I go here, I have the intercept, I have the main effects, I have the two-way interactions, and I have the three-way interaction. I can keep on going down. Let's see, here I have the intercept, I have the main effects, I have the two-way interactions, and I have the three-way interactions. And I can go through any column, any row, and every single column in the original design matrix is going to appear. So let's pick this one here. I've got the intercept, I've got the main effects, I have the two-way interactions, and I have the three-way interactions. So this happens every single time. All right, so now something else to notice is that this Cayley table is symmetric. Notice that this entry equals that entry, this entry equals that entry, this entry equals that entry, this entry equals that entry. I can keep on going here. This equals that, this equals that. Okay. So another thing that you will notice, that since I have like additional mathematical structure on this, is that when I multiply two things together, so if I take column A times column ABC, that's going to end up being BC. All right, so anytime I take a column and multiply by itself, that becomes the intercept, that becomes the identity, it does nothing to the result. And so anytime I make multiplication together, I cancel out anytime I have a pair equal to each other. All right, so it's kind of neat that we get this much mathematical structure in this abelian group going for us. All right, so look through, try to find a combination I missed. I didn't miss any, but you verify for yourself that this is the case. Down the road, we're going to use the group theory aspect of this to make more powerful partial factorial designs. All right, so now let's talk about other ways I can generate design matrices in R. Well, here I can use the expand grids functions using the list entry. Make this, I can either enter these guys directly into expand grid, or I could put them into a list. Either way. And notice I have to put the interactions manually, and I had to specify the intercept myself, which is right there. So notice I'm missing all my interaction terms, but this tells me what I would have for my main effects. If I'm just interested in what am I going to execute on my actual experiment, this doesn't tell me how I'm going to handle the interaction aspect yet. Now, model matrix, this is really nice in that this will work out a lot of stuff for us. And so the model matrix will take that expand grid that I did just a moment ago and put the intercept on it for us and put the interaction terms on there for us also. Boom, I got this easy peasy lemon squeezy. I like this one a lot. Now, we can also use packages that are designed for design of experiments. So the DAE, Design and Analysis of Experiments package, has a factor generation function. And here I give a list of factors. How many times does each uh, distinct combination appear in one run? How many times do I want to have all the runs appearing is the times. And then order, there's a default or Yates. Yates puts it in what I think is the more natural order. In general, we want to have it like in this format, where the one that is most important to us is to the far left, and we alternate on that one, is how I prefer to do it. Notice that I am missing my interaction terms completely. Now, this is the FRF2 is specialized for two-level factorial analysis. And this will actually do a lot of the work for us. This is especially powerful if I have a lot of factors I want to work with and want to be able to like tune things. This is a very powerful function for us to work with, and it has a lot of utility. Unfortunately, you'll notice that we don't get our interactions for us. It just tells us the levels to work with. We have to take that we have to do the interactions during our analysis step. But this is a very, very, very powerful function. Now we can also do the algorithmic design function, gen factorial, and this works out for us. Once again, I have to create the intercepts and interactions manually. All right, so why do we do this? Because we want the most bang for our buck when we do our experiments. Keep in mind that when I'm doing design of experiments, I'm in a situation where I can't do an unlimited number of runs. I don't have the time, money, and effort to go through and just generate tons and tons and tons of data. This is like the opposite of random number generation. Take the point of view that, how would I proceed if I had the budget for only 4 observations? If it was super expensive to get 1 observation to an experiment, what would I do to get the most information out of my results? All right. Well, that's all I've got for you. Life is short. Do math.